Let's discuss one-dimensional crystallography or one-dimensional space groups. So these are symmetry groups of certain patterns in space. The space we're thinking of is a Euclidean space, and we can give it coordinates x or y, and then the symmetry transformations will be affine. That is to say, the coordinates of the transformed point y are equal to m times x plus a translation. So this is an affine transformation. And since the pattern in space has to remain the same, these matrices M will be orthogonal matrices. And they will consist of transformations which are rotations as well as reflections. And T are just translations in Euclidean space. Now the group made of the transformations M, which appear in our group, that will generate the point group, which leaves the point y equal to 0 equal to x fixed. However, the point group is not a subgroup of the space group. Not necessarily. Because the translation T might depend on a particular matrix M to form a particular space group. So the point group is not necessarily a subgroup. Now, these space groups, or crystallographic groups, are classified by the dimension of Euclidean space in which we work. So the Euclidean space is uniquely determined by its dimension. But then also the space group will have a lattice subgroup, and the lattice itself also has a dimension, which we'll use to classify space groups. So the simplest case is a 1,1 space group, which are called line groups. Then we can have, for instance, in 2 dimensions with a 1-dimensional lattice, we will call this a frieze group. This is a symmetry of a frieze. And then, for instance, 2,2 are called wallpaper groups, and so on. Of course, the case of 3-dimensional space is particularly interesting, but we won't get there today. Here we'll discuss 1-dimensional symmetry groups. And there are basically 4 kinds. So if we are in the case where we're in 1-dimensional space and we have no translations, then the only possibilities are just a trivial group with only the identity element. So there is absolutely no symmetry. This is for a random pattern in 1-dimensional space. The second possibility without a translation is if we have a reflection. Indeed, this is the only orthogonal transformation in 1-dimensional space that is possible. So this would correspond to x goes to minus x with a fixed point in this particular coordinate system at 0. So this would be if we have a random pattern on one side, and then we have its reflection on the other side. Well, I can't draw this properly, but you see what I mean. This is when we have just a reflection symmetry. Now you can ask, what about the case when we have 2 reflections, say? Well, if we do have 2 reflections, like x goes to minus x and x goes to minus x plus a, which by the way has a fixed point at x equal to a over 2. Well, if we have both of these reflections, then x goes to minus x plus a, which is equal to x minus a, is also a symmetry, and therefore there is a translation amongst the symmetries. And if there's one translation, there's infinitely many, and therefore we are in the second class, which is given by 1, 1, namely a 1-dimensional Euclidean space with a 1-dimensional lattice symmetry. So here, the simplest case is clearly we have just a lattice symmetry, so a set of translations. So we have x goes to x plus a, and therefore x goes to x plus any integer times a. So the symmetry group in this case is z. Of course, the symmetry group in the reflection case was z2. So we have the trivial group z2, and now we have z. Now you can ask why not nz plus mz, but you can easily see that that's equivalent to another group which is isomorphic to z. You can also ask why not two incommensurate translations. Well, then you have the whole of R as your possible translations. So that would be just a homogeneous case. This is a case of just a homogeneous pattern. But if we restrict to discrete symmetry groups, then there's one more possibility. We can have a reflection, or the group generated by a reflection and translations. But this group would have an element x goes to minus x if the reflection is centered at 0, as well as x goes to x plus a. But this group is the generalized dihedral group in which z is a normal subgroup, and the quotient is equal to z2. All right, so we've had 4 cases. One is the trivial group, one is just a reflection, one is just translations, and one is the dihedral group, generalized dihedral group. These are all the one-dimensional symmetry groups if I don't take into account just a full R, all translations plus reflections. So then we can ask what, especially in these last 2 cases, what is the fundamental domain? We can also ask this in the first 2 cases. So the fundamental domain for a trivial group is just the whole line, the one-dimensional Euclidean space. Then we can take half of it for if we have reflections, all the positive numbers. For Z, the fundamental domain is a circle, and for the dihedral group, the fundamental domain is an interval. So what does this mean? What are these patterns? So in the first case, we have just any pattern, a random pattern on the line. In the second case, we already drew the pattern, just a random pattern on the half line. So now we can draw the interesting cases, which are 1, 1 with Z and 1, 1 with the dihedral group. So then the fundamental domain is a circle, so we can draw any pattern like this, and then just repeat it like that. I wanted this to be just repeated like that. We can draw any pattern like that is repeated in 1 dimension. I shouldn't have drawn this dot above. All right, then for the dihedral group, we have that the fundamental domain is an interval. So how does that work? Well, we draw any pattern again on an interval, but then we must reflect it. And then we can start repeating this pattern over and over again. And this is a pattern in 1 dimension, which has the symmetry group, the generalized dihedral group. So these are the simplest 1-dimensional examples of crystallographic groups.